All right, we're going to finish up our absolute value problems, and then we'll start with some, we'll do some inverses, okay? We're going to do absolute value and inverses. I stopped on this slide. I said we're going to kind of skip it, but I do want to go through this one. So if you're looking at your page, it's like at the bottom lower left of one of the pages. I do want to go through this one. So we're solving absolute value. ISO the absolute value first. Did I get there in time? No. Wait, yes. No. Oh. All right, so ISO the absolute value. I should probably bring that mouse with me so that way this doesn't happen again. ISO the absolute value. Say it 5 times. It'll make it true. So I get 2 times x minus 1, negative 6. Divide by 2. X minus 1 absolute value is negative 3. Now, from here, a lot of us get in a habit. Set up the 2 equations, the positive and the negative. Now, here's my question for you. Can an absolute value ever be negative? No. So this right here, once you get to this step, is no solutions, okay? So be careful if you start plugging along and you're just like, oh, every time I set up the 2 equations, every time I set up the 2 equations. It's kind of the same thing. We will, never mind. I'll hold off on that one until we get there. Don't want to overburden you. All right, how do you solve inequalities? Inequalities are the exact same way as equalities. We're going to set up 2 equations, one positive, one negative. But the negative one, we flip the sign. Okay? So, ISO the absolute value is greater than or equal to 10. So it's by itself. I can set up my 2 equations. Equation 1 is greater than or equal to 10. Equation 2, there's a negative 10 involved, and then I flip my sign. Okay? So once I get the absolute value by itself, I still have my 2 equations. Not the same sign, though. We got to flip it. Right away. Yep. When you make your 2 equations, the negative one, flip the sign. I'm going to add 2. So now here it's just good old-fashioned algebra fun. If this isn't fun, what is? Exactly. So those are my 2 equations. What would that graph look like? X is greater than or equal to 12. You do have a question with the graphing on it. So 12 to infinity. And x is less than negative 8. Looks like that. Okay. When you go do the homework, it's not going to be marked out exactly. It's just going to ask which graph would it look like. Does it look like the oars? Does it look like 2 directions? Or is it going to be not connected? Okay. You don't need to write the infinities in. I do just in case we ever need to convert it to interval notation, right? Which I don't think I had to do yet. All right, let's try this wretched beast. ISO the absolute value. Two equations now. Always 2 equations. X plus 1. Keep it the same and make it different. So flip it, negate it to a negative. Okay? So I get x is less than 15. X is greater than negative 17, right? Now when I go to graph this one, it's not going to look like this. Because when I go do it, x is less than 15, x is smaller than 15, it's going to go this way, right? X is greater than negative 17, though. There's a negative 17 here, and it wants to go this way. So do they overlap? So we graph the overlap, okay? If you are a person who doesn't want to like graph each time and think about it, there is a set rule that works all the time. If your absolute value is less than a number, absolute value of x is less than a number, it's always going to be like the barbell, just the one straight across. And if you get x is greater than some number, it'll always be the handlebars, like the two edges. It'll always be that way if you don't like to think it through and like actually go through and graph it each time. All right. So treat these just like we did in 2.7. We're just making two of them. You just added one more step. If you really want to think about it, you can actually set these up as an AND equation like that and do them as well, if that's what you want to do. But you don't have to. All right. That one. This one I'm going to do this one I can do without any math. Well, very little math. Here's my question for you after I ISO this. Whoopsie, math is tough. Absolute values are always what? Are they positive or negative? Are you sure? Positive. All right. So will this ever be less than -2? Will an absolute value ever be less? No. So this is going to be all real. If you ever get an inequality with an absolute value greater than 0 or greater than a negative, it's automatically all real because an absolute value cannot give you out a negative. It cannot be less than 0. Okay? So that one's always true. I just divide by 5. Now, oopsie. Now, can an absolute value be negative? No. So can it ever be less than -2? No. So this is no solutions. Okay? This is also, if you ever get absolute value of x is greater than a 0, or that's not a set rule, but if you ever get absolute value greater than or equal to anything less than 0, it's automatically always going to be true. All right? On the next slide, if you would like to try these and watch the Webster video, by all means, pause it, try it. It's just like these examples. ISO. Be careful. Just remember when you divide by a negative, what you have to do to your sign before you flip it. Or I mean before you do your 2, you got to flip it. Don't forget when you divide or multiply by a negative, flip your sign. All right. This is a review slide. We've actually seen it before. I'm going to jot a little note over here to remind me. When I'm looking for y-intercepts, this is good review too for the test because it'll come up. We had to do it for a few different functions earlier. If I'm looking for a y-intercept, you set x equal to 0, right? And then solve. That's what this is saying. Slove? Not enough coffee. If I'm looking for my x-intercept, set y equals 0, then solve. Does that ring a bell? So there will be some questions on the test and on the homework. You have to find your x and y intercepts of different functions. The nice thing is all throughout the year, this is always what we do for x and y intercepts. It'll work for any function, anytime, all the time. All right? This is what this is all saying. It's a review of what was It might be verbatim what was on earlier section slides. Okay? So let's graph this by hand. You are not going to be using Desmos on the test because it's made in a way that you don't need Desmos for any of it. The graphs are given to you if given. I want to make sure that you can find X and Y intercepts without using a graph. These ones aren't too bad though. I would put this in your memory bank that a normal y equals absolute value of x looks like a v, right? Starts at 0, 0. Correct? So put that in your memory banks. So if we wanted to just quick sketch this to get an idea of what's going on, what's this minus 3 doing? That's going to go right 3. And the minus 5 is going to tell us to go down 5. Right? Right 3, down 5. So that's going to be, this is just a sketch. It's not going to be accurate, but that's going to be about what that graph looks like, right? I moved right 3 and down 5. Now, I could kind of draw it and guesstimate and get my intercepts, but let's make sure we know how to do it right. So for my y-intercept, I'm going to plug x equals 0 in, right? I'm going to do y equals 0 minus 3 minus 5, right? Absolute value of negative 3 is 3 minus 5 is negative 2. Which, in my quick sketch, I was pretty close, actually. So just doing it, we'll do that. Negative 2. So we have the point 0, negative 2 on that graph, right? For my x-intercept, I'm going to set y equals 0. Remember, f of x and y are the same thing. They're interchangeable when I'm doing this. So I'm going to do 0 equals absolute value of x minus 3 minus 5. All right, add my 5 over, isolate that absolute value, and then set my two equations. Because how many x-intercepts are we going to have on this when you just look at it? How many do you think it's going to cross? 2. So for absolute value, you can either have 2, 1, or none. Right? The original one had 1. This one's going to have 2. If I move it up, what's going to happen? It's not going to hit. It's not going to hit anything. So negative 5 equals x minus 3. 5 equals x minus 3. So negative 2 equals x. Yeah, I did that right. And 8 equals x. 2, 0. 8, 0. So now I'll call that negative 2. Call that 8. Okay? Take a second, digest it, take a sip of your coffee. Again, this is true for any function we will ever do. Okay? This is the way to do it. All right, let's do this one. This one will save us some math, though. We're going to have to do a little bit less math. Because I'm going to sketch the transformation so I can kind of see what's going on. I'm going to go right 8 and up 10, right? Uh-oh. Whatever. My graph's going to be up here, isn't it? So right away, Will that ever cross the x-axis? No. So there will be no graph or no x-intercepts. Okay. So that saves me a ton of time. Do I have a y-intercept? Yes, I do. No matter what, it's going to cross that at some time. So to find my y-intercept, x equals 0. 2 times 0 minus 8 plus 10. That same thing as 2 times positive 8, right? Because of absolute value. 26. All right. That's a wild one. Yeah, so that's my y-intercept. Don't worry about sketching the graph on this as much. If you can find intercepts, you can tell me a lot about the graph. Okay. Again, we're not finding x-intercepts because I already know that there are none. And you would approve, if you set this equal to 0, you subtract the 10 over, and then right away you say, can an absolute value equal negative? No. So it's no solution. So even if you tried to do it, and you said it was equal to 0, it still would not work. So if you go to find an x-intercept and you get something that doesn't work, there's not going to be an x-intercept. That happens with quadratics as well, right? Quadratics can do the same thing. Those parabolas from a long time ago. All right, I think that's it for this section. Again, you can try that one. That's an extra example. It is posted. One more. Inverses. I'm very much giving you the Cliff Notes of inverses, okay? I'm going to give you the very Cliff Note versions of inverses. If you want to watch the whole thing, by all means, you can go to it. I'm going to make sure that we can get through. You have a basic understanding of inverses. Sound good? You guys have been using inverses your whole life. You just don't call them that. How would I get x by itself? Because adding 3 is the inverse of subtracting 3. An inverse is something that gets you back to the original, okay? So a long time, if you took geometry back in the day, we used those cosine, tan, and sine inverse, the -1 things, to reverse sine, cosine, and tangent. If you see x squared, how do you get x by itself? Square root it. Square rooting is the inverse of squaring. Okay, so you've been using actual inverses pretty much your whole algebraic career. Now we're going to get the tools to be able to find inverses. Don't worry about it. All this is saying that if I plug a function into its inverse, I get out x. And we just talked about it. So like, if f of x is x squared, you guys told me the inverse of that is square root of x, right? And does it work? Is square root of x squared x? Yeah. Is it true both ways? Because it has to be true both ways. Is square root of x squared x? Yep. That's an inverse. That's all it's saying, is that it takes it back to the original. I'm only going to make you do a little bit with that definition. There's a cool thing. There's a thing. Oh. Now. Ooh, that was tricky. So, now for a function to have a legit inverse, it has to be 1-to-1. What does it mean to be 1-to-1? We briefly touched on it a long time ago. 1-to-1, we made it past the horizontal line test, right? We made it past the horizontal line test. Okay, so like, determine if these functions are 1-to-1. 3x minus 4 When I graph that, that's just a straight line, correct? It's not a quadratic. Is that 1 to 1? Does it pass no matter where? Ooh. If I draw a horizontal line across it, does it only hit at one point? Yeah, so that's 1 to 1. Yes. What about x squared? X squared looks like this, right? Is x squared 1 to 1? No. No dice. But Mr. Twilliger, you just told me the inverse of x squared is square root of x. Now that's cap, bruh. I hope in 10 years someone watches this and has no idea what I just said. I'll talk about how we can do that in a slide. What about, what's absolute value functions look like? They look like these, right? Is that 1 to 1? No, because I hit more than once. And we also know when I go to solve that, I always set up two equations, right? If I'm setting up two equations, that's no good. 3D. All right, so, and then x minus 9 is another straight line. That is 1 to 1. Okay. So these are the really basic ones. You should be able to do these ones without graphing because they're just basic, linear, quadratic, absolute value, linear, right? Now, if you get ones like these, it's okay if you have to graph these and take a look at them and see if they're 1 to 1. That's okay. But actually, so determine whether or not it's 1 to 1. So let's say, like I said, you're struggling to know. You will get a graph for these, or you can graph them. Okay. Let's graph the one and see what it looks like. So what we got, x to the 3 minus 2x. All right. That's what that one looks like. Oopsie doodles. Sorry for my language. Is that 1 to 1? No. Hits more than once. What's the other one? X to the 3rd minus 4. Is that one 1 to 1? This one is. I know right there it looks like, if I zoom in really, really close. Oh no, Desmos, don't let me down. There is going to be, all right, Desmos, you're not supposed to do that. It is 1 to 1 because x to the 3rd is. It looks like it's not. Come on, man. But anyway, x cubed is definitely 1 to 1. And, ooh, what's 1 divided by parentheses? Was it x minus 4? 3. Same difference. Is this one 1 to 1? It is actually. Because when you look at it closer, it'll slowly go down. That one is 1 to 1. 1 over x is 1 to 1 as well. All right. All right. Uh-oh. What do I do if one's not 1 to 1? Does that mean there's no inverse that could ever be possible? Kinda, but we can restrict the domain. So I'm not going to make you tell me how you would restrict the domain to find an inverse. That's higher up math. What we're just going to say is we can find the inverse on the domain. Or we're going to just say, hey, if we restrict the domain, we will have an inverse. Okay, you don't have to find what domain it works for. Okay, so yep, you just say on. We'll just assume it's on the right domain to find the inverse. Okay, you don't have to find it. So let's check if two things are inverses. We're actually, it's gonna be really close. I might be able to finish everything today. All right, let's check if these things are inverses. To check if they're inverses, you plug them into each other. okay? And you have to go both directions. You're pretty much the Travis Hunter of functions. That'll be topical for a long time, I believe. So I plug these into each other. I skipped a few slides. So remember, that means f of g of x, right? G of f of x. And what happened when I took square root of x squared? What did I get? X. So what do I need to get out? X. It needs to be by itself. Okay? I need to get it by itself. I skipped a bunch of slides. So let's try it. I'll do the f of g of x first. So f of, I'm plugging in g of x into here. You don't have to write out every step like I'm going to do. You could kind of think about it right away. I'm just going to take this and put it in for x, right? That's what I'm going to do. Wherever I see an x, plug in that. Okay? Plug her in. What do I need to get? X. Everything needs to cancel, like my favorite shows. So 5 times 0.2 is 1x. 5 times 40 is 200. Does this cancel out? No. So these were not inverses. I need to just get x by itself. X is not by itself. If x is not by itself, it's not an inverse. Everything. I'll show you an example of when it is an inverse. If you want to try this one on your own accord, this one is also not an inverse. It does not work. I could show you here, let me show you a basic one. Let's say f of x is x plus 2, and g of x is x minus 2. So if I plug in this for x, right, I would get x minus 2 plus 2, which is x. You need to get just x by itself. You have to do both. So I'm halfway there. This one I didn't have to do the other side because if one side doesn't work, the whole thing doesn't work. So then for this one, I would have to do the x plus 2 minus 2, which is also x. It has to be true both directions. Now, majority of the time, if it's true one way, it's true the other way. You're usually all set. Very rare. You don't see it true. Like if it's true one way, it's not the other. Let's try and remember, right? A lot of these, let's do this one. This one's good. Let's check this beast. So I have to do f of g of x, and I have to do g of f of x. You have to do both. I'm going to go a little bit. So I'm going to take this brown one and plug it in for x, right? I'm going to color coding. This is a good color combo. If anyone's looking for like prom dress colors that go together, this would look good. Wedding dress colors, green and brown. It's kind of camo. That'd be kind of cool. No one see you come down the aisle. All right, so let's check it. Distribute 2 times 0.5 is 1, so that's good. 2 times negative 6 is negative 12 plus 12. What happens to these? They cancel. So that side is good. X is by itself. Okay. Now we have to try the opposite. We're going to put the green into the brown one. We'll keep it consistent. So 0.5 times 2x plus 12 minus 6. 0.5 times 2 is 1. 0.5 times 12 is 6. So I got x on both sides. So that one is, yes, inverse. Yeesh. With the multiplication and adding ones, if it's true one way, it's going to be true the other way. It just the way it is. Oh, I forget if I give you guys like cube roots. I want a square root one. Where's a good square root one? Oh, that one. All right, so sorry I'm skipping some of these. Some of these are just, this one's a no. That one's going to also be non-inverse if you want to try it out. That one does not work. All right, let's do these ones. These ones are good. These ones are good. You guys want to stick with the green and brown? I think these are pretty nice colors. All right. I wish have you guys ever seen there's people who can do math with both hands with 2 markers on a board? No friends. No, I'm just kidding. They might have friends. They won't watch this. They don't need to. All right, so we need to do our f of g of x and our g of f of x. So again, I'm going to plug my brown into my green and see what happens. Okay? So I'm going to do square root of x minus 9 squared plus 9. Okay? Now be careful. When I go to do that, can I just cancel or put that 2 into both parts? No, this is actually one of these things, right? Now here's my question. If I FOIL that out, is there any shot at all that it's going to cancel out? Well, what's negative 9 times negative 9? 81, right? Is 81 going to cancel out with 9? No. So do I have to do the whole thing, or at this point can I look at it and kind of think like there's no shot that this is going to be an inverse? Yeah, this is absolutely not. You could, if you needed to, you could FOIL it out. But I just know because these last 2 terms are going to be 81, right? Negative 9 times negative 9. And 81 and 9 aren't going to cancel out. There's no way you're going to, how about this? There's no way you're going to FOIL this out and it's going to cancel. If you can't see it, you can FOIL it out. But there's no shot. Is that something the kids would say? Okay. I'm hip. Let's try this one, though. We'll do our green and brown. So I'll plug the brown in the green and the green in the brown. I should have done this before when we're doing the function stuff. Oh, minus 5. All right. So I'm going to plug in my 4th root of x plus 5. Now this one's different. I have a 4th root into a 4. Now, some of you are probably thinking x to the 4th is not 1-to-1, Mr. Terwilliger. This doesn't have an inverse. This is a trick question. Many of you are like, what are you talking about? And that's okay too. Remember, we're going to just add that to this so that way there will always be an inverse. You see that? There will be an inverse. What's 4th root to the 4th? It's kind of like what's square root to the 2nd? They cancel, right? They are inverses. So if I see these, they just go away. Because it's the opposite. Like I not cube, there's no name for it. I'd 4th root something to get rid of the 4th power. So I got x. So I put brown and green. I have to do green into brown. Man, I hope no one watches this. It's just not good. Right? I'm plugging in. Now there's nothing on these parentheses, right? So I'm just going to do my addition. What's negative 5 plus 5? Cancels. What's the fourth root to the fourth power? Cancels. It's x. Is an inverse. Is an inverse. Perfect. We are actually doing great. How do you find an invert? Oh, look at this beautiful green-brown rainbow across the clouds. If you're colorblind, that might be what you saw. I actually had a buddy who's colorblind, and he could not tell the difference. His was red. He could not tell the difference between red and brown at all. Like, they looked exactly the same. Like, I have a really good story about that. I can tell you someday. All right, so how do I find an inverse? The slide above told us kind of how, but I'm going to give you the Mr. T definition. Switch. You're going to switch your x and y, then solve. That's it. Okay? You switch your x and your y and you solve, and that will give you the inverse. That will work every time. You switch your x and your y and you solve. Because you're working backwards and you're figuring out how to work backwards. So I'm going to switch my x. Remember, when I see... Now, you could write... Technically, book says you write like the g prime of x and you go through and solve it. No one does it. Everyone uses y just because it's a lot less writing and it's a lot easier to solve it. There's less parentheses. So remember, I can think about this as y equals that, right? So switch them. When I go to find my inverse, I'm going to say x equals 3y minus 7. Okay? And then when I get that solved, I have my inverse. I need to get y by itself. Add 7. X plus 7 is 3y. 5 by 3. Just leave it as a big old fraction. That's great. So x plus 7 over 3 is my y. Now let's be really cool here. I could call that my g inverse of x. Okay? That's how you do it. Switch your x and your y and your solve. Let's do this one. Switch my x and y. So I'm going to write it as x equals 4 times y minus 2 to the third. I switched them. Outside to inside, right? Like an onion. Because it also makes you cry. So I'm going to divide first. How do you get rid of something to the cube? You cube root it. Okay? Cube rooting cancels your cubes. So cube root of x over 4 equals y minus 2. This is one of the tougher ones you would see. Get rid of the 2 by adding 2. I might have to draw an arrow. That's my inverse. That one was tougher. There might be one like that because honestly, it's a lot of algebra skills. Yeah, I would write that one down. That'd be great. Or could have came to the wind time yesterday. All right, so here we go. Let's do one more and then we're done. We're actually exactly where I need to be. Let's do this beast. First step, switch my x and my y. Just remember, take everything step by step. Just go slow is smooth and smooth is fast. Slow is smooth and smooth is fast. What's my thing farthest away from my y? The 8. So I'm going to subtract 8. Right? Oh, did I write this down wrong? Thank you, guys. It's my first day. What's my furthest thing away from y now? Y is in this little house. The 5. This may look, don't overthink these problems. They look really complex. You're just doing solving that you've been doing your whole life, right? You start from furthest away, you move closer into it. It just looks different. How do you get rid of a square root? Square it. It's just going to look messy. You know what? Life's messy. We just got to figure it out. That's my Bob Ross moment for you guys. How do you get rid of that plus 3? Subtract it. There you go. Okay. Was there any step here that was brand new that we've never seen before in your life? Square adds, it was just a lot. We just had to do 5 steps, right? Slow is smooth and smooth is fast. Slow is smooth and smooth is fast.